So why am I interested in novel anesthetics? And what I want to highlight here is that this is general anesthesia, not local anesthetics, which are just providing a sort of topical anesthesia. This is where somebody is inhaling an anesthetic, or they can be injected with an intravenous agent, which renders them unconscious during surgery. The first public demonstration of anesthesia was at Mass General Hospital. There was an anaesthetist there, William Morton, who administered ether to a patient, Gilbert Abbott. He had a tumour on his neck, and there was a surgeon there, Dr. Warren, excised the tumour under the ether anaesthesia, and the patient knew nothing of it, and so this was the first public display at the Ether Dome. The interest in novel anaesthetics is that some of these anaesthetics, although very good and very, very effective, and incredibly, in terms of being therapeutic agents, probably some of the most widely used, they do have some potential downsides, and they do have some potential side effects. And some of those side effects can be really quite dangerous. One, propofol can induce this disorder called metabolic acidosis, basically a lowering of the pH in the blood, which can be extremely detrimental, if not life-threatening. And also some of the inhaled agents, isoflurane, sevoflurane, have potential impact on the liver. And so there's always this call to generate new anesthetics that don't have some of these sort of unpleasant and potentially sort of life-threatening complications. So I was working in London at Imperial College doing my postgraduate work, and I was actually working on a project that was involved in snake toxins and looking at how snake toxins impact the nervous system. And once I finished my thesis, I made a lateral move using many of the same techniques that I'd used in my postgraduate work into the biophysics section at Imperial College under two mentors and supervisors. They were Nick Franks and Bill Lieb. Their interests were in anesthetic mechanisms and how anesthetics, and as I say, general anesthetics rather than local anesthetics, and how those impact brain function. The thought to that point was that anesthetics in some very non-specific way were delivered to the brain, and what they did was they caused cell membranes, in other words neuronal membranes, because we're dealing with the brain, to become more fluid. So the membranes somehow became a little bit more fluid in the presence of the anesthetic, and that was by some miracle able to render you unconscious during surgery. They took this to task and recognized that there were many more specific targets for the anesthetics in the brain, and what they recognized is that there were specific receptor targets that were acutely and very potently modulated by the anesthetic action. They focused in, at least at the time I was in the lab, on receptors called, or receptor proteins called GABA receptors, and other receptors that were called glutamate receptors. And this big contribution was that they shifted all of the focus from the membrane fluidity, in other words interaction with the lipid membranes, to specific interactions with protein receptors. So at Smith, what I've been focusing on is really an extension of that GABA receptor work. And the first thing I did when I arrived was set up some of that electrophysiology and electrophysiology recording systems so that we could look at GABA receptors again and start to ask questions about sort of modulation by anesthetic agents. I had a sort of interesting conversation with Lali Burke, who's a professor emeritus in chemistry. And it was just one of those things in passing in the corridor. We just were discussing different, well, she's an expert in plant extracts and plant chemistry, and we were discussing monoterpenoids, and a particular monoterpenoid, which is menthol, which is derived from the peppermint plant. Menthol and a lot of its derivatives, there are a lot of monoterpenoids, sort of alcohols, borneols and other camphor. Many of these are positive modulators of GABA receptors, just like propofol is in terms of its interaction. And of course, propofol is a very commonly used intravenous anesthetic in medical practice today. So we started to look at the structure of menthol and started to generate derivatives of menthol. And this work was mainly done in collaboration with a lab at University of Florida who synthesized some of these compounds. But more recently, I've been collaborating with the Shea lab at Smith in the chemistry department, and Kevin Shea's lab has also been isolating some isomers of what are menthol derivatives, these cyclohexanols. And so we're starting to hone in on what structures might be important for producing, one, this positive modulation of GABA transmission, in other words, enhancing inhibitory neurotransmission, but ultimately with the goal of extrapolating to that to agents that would be better general anesthetics.